Myself, Dr. Sachin Kumar, welcome you in lecture series of Module 3 Differential Calculus 2nd. My topic of today lecture is partial derivative 2. In this lecture, I will discuss introduction to total derivative, composite function and its derivative, implicit function and its derivative, and problems of total derivative. So let us start with introduction to total derivative. If u equals to fxy be any function in two variables xy, and if del x del y are small increment in values of x and y respectively, then del u corresponding change in the value of dependent variable u is given by del u equals to f x plus del x y plus del y minus f xy. Now rewriting this term, we get del u equals to fx plus del x y plus del y minus f x y plus del y plus f x y plus del y minus f x y. We add and subtract f x y plus del y in the previous term. Now combining first two terms and dividing and multiplied by del x. Similarly combining last two terms and dividing and multiplying by del y, and then taking limit delta x tends to 0 and limit delta y tends to 0, we get du equals to del u by del x dx plus del u by del y dy, which is called total derivative of function u equals to fxy. Similarly, if u equals to fxyz, that is u is the function of x, y and z, then total derivative du equals del u by del x dx plus del u by del y dy plus del u by del z dz. Now composite function and its derivative. If u equals to fxy, where x equals to phi t, y equal to omega t, then u is called a composite function of single variable t, and its value of total derivative is given by du by dt equals to del u by del x into dx by dt plus del u by del y into dy by dt. Clearly in this relationship, partial derivative of u with respect to x and y are appearing, since u is the function of two variables x and y, and ordinary derivative of x and y with respect to t are also appearing, as x and y are function in single variable t. Now since u is composite function in single variable t, so its derivative with respect to t is represented by ordinary derivative. Also, if z equals to fxy, where x equals to phi uv, y equals to omega uv, then z is called a composite function of two variables uv, and the value of total derivative of z with respect to uv are given by del z over del u equals to del z over del x into del x over del u plus del z over del y into del y over del u, and del z over del v is equals to del z over del x into del x over del v plus del z over del y into del y over del v. Here it is quite evident to see that del z over del u, del z over del v are total derivative of z with respect to variables u and v. Since u is the composite function in more than one variable, so derivative of z with respect to u and v are also taken as partial derivative. Now we discuss an example. If u equals to x cube plus y cube, where x equal to a cos t, y equal to a sin t, find the value of du by dt and hence verify the result. Here we have u equals to x cube plus y cube. Clearly u is the function of variables x and y. So derivative of u with respect to x and y will be partial derivative, where x equals to a cos t, y equal to a sin t. So from equation 2 it is clear that x and y both are function in single variable t. So derivative of x and y with respect to t will be ordinary derivative. Also from equation 1 and 2 we conclude that u is a composite function in single variable t. So in this case we shall have du by dt equals to del u by del x into dx by dt plus del u by del y into dy by dt. So in order to get value of del u over del t, we require partial derivative of u with respect to x and y and derivative of x and y with respect to t. So from equation 1, differentiating u partially with respect to x, we shall get del u over del x equals to 3x square, as function of y will be treated as constant, and del u over del y equals to 3y square, as function of x will be constant. Similarly, from equation 2, dx over dt will equals to minus a sin t, and dy by dt will equals to a cos t. Putting values of all these derivative in equation 3, we get du by dt equals to 3x square, value of del u by del x, into minus a sin t, value of dx by dt, plus 3y square, value of partial derivative with respect to y, into a cos t, value of dy by dt. Now if we put values of x and y from equation 2 and simplify further, we get du by dt equals to 3a cube sin square t into cos t minus cos square t into sin t. Again, to verify the result, we shall put values of x and y from equation 2 in equation 1 and receive value of u in terms of t directly, which will be u equals to a cube cos cube t plus a cube sin cube t. So differentiating both sides with respect to t, we shall get du by dt equals to, now in both terms a cube is common, we take it common, and differentiate cos cube t with respect to t, we get 3 cos square t into minus sin t, and differentiating sin cube t, we get 3 sin square t into cos t. So from here, du by dt becomes 3a cube sin square t into cos t minus cos square t into sin t. From equation 6 and 7, we observe that both values are same. Hence, the value of du by dt obtained by the concept of composite function is equal to value of derivative obtained by direct method. Hence, the verification of the result. Next example, if v equal to f 2x minus 3y, 3y minus 4z, 4z minus 2x, compute the value of 6vx plus 4vy plus 3vz. Here we have given that v equal to function of 2x minus 3y, 3y minus 4z, 4z minus 2x. To obtain required value, we redefine v to be a function in R as t initially, where R equals 2x minus 3y, s equals 3y minus 4z, t equals to 4z minus 2x. Also differentiating equation 2 partially, we shall get partial derivative of R, s and t with respect to x, y and z as del r over del x equals to 2, del r over del y equals to minus 3, del r over del z equals to 0. Del s over del x equals to 0, del s over del y equals to 3, del s over del z equals to minus 4, and del t over del x equals to minus t, del t over del y equals to 0, del t over del z equals to 4. Now, since u is a function in 3 variables r s t, where r, s and t each are function of x, y, z, so v will be a composite function in 3 variables x, y, z. So applying the concept of composite function, vx, which represent del v over del x, is given by vx equals to del v over del r into del r by del x plus del v over del s into del s by del x plus del v over del t plus del t over del x. Now putting value of del r over del x, del s over del x, del t over del x from equations 3, 4 and 5, we get vx equals to del f upon del r into 2 plus del f upon del s into 0 plus del f upon del t into minus 2. On simplification, we get vx equals to 2 into del f over del r minus del f over del t. Now vy, which is the value of del v over del y, will be del v over del r into del r by del y plus del v over del s into del s over del y plus del v over del t into del t over del y. Again putting the values of partial derivative of rst with respect to y, we get vy equal to del f over del r into minus 3 plus del f upon del s into 3 plus del f upon del t into 0. On simplification we get vy equals to 3 into minus del f by del r plus del f by del s. At last vz equals to del v over del r into del r over del z plus del v over del s into del s by del z plus del v over del t into del t over del z. Now we put value of partial derivative of rst with respect to z from equations 3, 4 and 5 and get vz equals to del f upon del r into 0 plus del f over del s into minus 4 plus del f over del t into 4. On simplification we get vz equals to 4 into minus del f over del s plus del f over del t. Now using equations 6, 7 and 8, value of 6vx plus 4vy plus 3vz will equals to, in each term we shall have 12 common, we take 12 common and inside the product we get del f over del r minus del f over del t plus minus k del f over del r plus del f by del s plus minus del f over del s plus del f over del t. We can see clearly that del f over del r will cancel with minus del f over del r, minus del f over del t will cancel out with del f over del t and plus del f by del s will cancel out with minus del f over del s. So on simplification we get 6vx plus 4vy plus 3vz equals to 0. Next example, if u equal to u y minus x over xy, z minus x over xz, then so that x square del u by del x plus y square del u by del y plus z square del u by del z equals to 0. Here we have u equals to function of y minus x over xy, z minus x over xz. So here we define u to be a function in R and S initially, where value of R equals to y minus x over xy, simplifying which we get R equal to 1 upon x minus 1 upon y. Also s equals to z minus x upon xz. On simplification gives s equals to 1 upon x minus 1 upon z. If we differentiate equation 3 partially with respect to x, y, z, we get del over del x equals to minus 1 upon x square. Differentiating this term partially with respect to x, treating y as constant. Similarly del r over del y will be 1 over y square and del r over del z will become 0 as this term doesn't contain z and xy will be treated as constant. And value of partial derivative of s, that is del s over del x, from here will be minus 1 over x square. Del s over del y will be 0 as there is no term of y, and del s over del z will equals to 1 over z square. Now by the concept of composite function, derivative of u with respect to x will be given by del u by del r by del x plus del u by del s into del s by del x. Putting values of partial derivative of r and s with respect to x, we get del u by del x equals to del u by del r into minus 1 upon x square plus del u by del s into minus 1 upon x square, which on simplify gives value of x square del u by del x equals to minus del u by del r minus del u by del s. Now del u over del y will be given by del u by del r into del r by del y plus del u by del s into del s by del y. Putting value of partial derivative of r and s with respect to y, we get del u by del y equals to del u by del r into 1 upon y square plus del u by del s into 0. On simplification, we get y square into del u over del y equals to del u by del r. Similarly, del u by del z will be given by del u by del r into del r by del z plus del u by del s into del s by del z. Putting value of partial derivative of r and s with respect to z, we get del u by del z equals to del u by del r into 0 plus del u by del s into 1 over z square. On simplification, we get z square into del u by del z equals to del u by del s. So adding equations 4, 5 and 6, we get x square del u by del x plus y square del u by del y plus z square del u by del z is equals to minus del u by del r minus del u by del s plus del u by del r plus del u by del s. From here it is clear that on simplification we get x square del u by del x plus y square del u by del y plus z square del u by del z equals to 0. Next example, let z be a function of u and v and uv be the function of two other variables x and y such that u equals to lx plus my, v equal to ly minus mx, so that del 2z over del x square plus del 2z over del y square equals to l square plus m square into del 2z over del u square plus del 2z over del v square. Here we have z to be a function of u and v, where u is given by lx plus my, v equals to ly minus mx. From equation 1 and 2, it is clear that z will be a composite function in x and y. Now differentiating equation 2 partially, we shall get del u by del x equals to l, del u by del y equals to m, and del v by del x equals to minus m, del v over del y equals to l. Now by concept of composite function, del z over del x will equals to del z by del u into del u by del x plus del z over del v into del v by del x. Now putting the value of partial derivatives del u by del x and del v by del x, we get del z over del x equals to l del z by del u minus m del z by del v. Similarly, del z over del y will be equals to del z over del u into del u by del y plus del z over del v into del v over del y. Putting values of partial derivative of u and v with respect to y, we get del z over del y equals to m into del z over del u plus l del z over del v. From equation 3 and 4, one can get value of equivalent operator as given below. Equivalent operator to del over del x will be l del over del u minus m del over del v, which can be obtained from equation 3 just eliminating z from equation 3. Similarly, from equation 4, del over del y will equivalent to m into del over del u plus l into del over del v. These two equivalent operator will be useful for us in next step. Now to find del 2z over del x square, we need to differentiate del z over del x with respect to x again. So if we differentiate equation 3 with respect to x on both sides, RLHS will be del 2z over del x square, but in RHS we shall have del over del x of l into del z over del u minus m into del z over del v. Now in RHS we are having partial derivative with respect to u and v. So we replace del over del x by its equivalent operator in such a way that del 2z over del x square equals l del over del u minus m del over del v into l del z over del u minus m del z over del v. Now we shall operate first operator over second term and simplify, then second operator on the second term and simplify. After doing this and collecting the same derivative term, we shall get del 2z over del x square equals to l square del 2z upon del u square minus 2lm del 2z upon del u del v plus m square del 2z over del v square. Similarly, differentiating del z over del y on both sides with respect to y, we shall get del 2z over del y square equals to del over del y of m del z by del u plus l del z by del v. Since in RHS we are having partial derivative with respect to uv, so we replace del over del y by its equivalent operator in such a way that del 2z over del y square equals m del over del u plus l del over del v into m del z over del u plus l del z over del v. Simplifying this also, as in previous term, we get del 2z over del y square equals to m square del 2z over del u square plus 2lm del 2z over del u del v plus l square del 2z over del v square. Now adding equation 6 and 7. To add equation 6 and 7, we add del 2z over del x square plus del 2z over del y square and get the LHS as here. Now in RHS we shall add up first term of both equation. If we add these two terms, del 2z over del u square will be common and we shall get l square plus m square into del 2z over del u square. Similarly, adding last term of both equation, we shall get l square plus m square into del 2z over del v square. From equation 6 and 7, we are clear that these two terms, second term of both equations, will cancel out as they are having same value with opposite sign. Now further we can take l square plus m square common from here. If we did so, we get del 2z over del x square plus del 2z over del y square equals to l square plus m square into del 2z over del u square plus del 2z over del v square, which is the required result, hence proved. Next we are going to discuss concept of implicit function and its derivative. For any implicitly defined function fxy equal to 0, its total derivative will be 0, as RHS is 0. But we know total derivative of fxy is given by del f over del x dx plus del f over del y dy. So this total value will equals to 0 as RHS is 0. From here we can find value of dy by dx, and the value of dy by dx will equals to minus del f by del x upon del f by del y. If we replace this notation by fx and del f over del y by fy, we got dy by dx equals to minus fx over fy. Similarly, if we differentiate it again with respect to x, we get this formula of second order derivative of y with respect to x, that is d2y over dx square equals to fy whole square into fxx minus twice of fx into fy into fxy plus fyy into fx whole square upon fy whole cube. Here fxx means second order derivative of f with respect to x. Fyy means second order derivative of f with respect to y, while fxy means del 2f over del x del y. Now take an example. If x cube plus 3x square y plus 6xy square plus y cube equals to 1, find dy by dx. Clearly fxy will be a implicitly defined function given by fxy equivalent to x cube plus 3x square y plus 6xy square plus y cube minus 1 equals to 0. Differentiating equation 1 partially with respect to x, we shall get fx equals to, from first term we shall get 3x square, from the second term 3y will be constant, will be outside the differential operator, and a derivative of x square will be 2x. So overall value from second term will be 6xy. From the third term y square will be treated as constant, derivative of x with respect to x will be x, so we shall get 6y square, and last two terms will give 0. So fx will equals to 3x square plus 6xy plus 6y square. Similarly, derivative of f with respect to y treating x as constant will be given by 3x square plus 12xy plus 3y square, which is obtained from here by differentiating partially with respect to y treating x and function of x as constant. Putting all these values of both partial derivative in this formula of dy by dx equals to minus fx upon fy, we get dy by dx equals to minus 3x square plus 6xy plus 6y square upon 3x square plus 12xy plus 3y square. Here we observe that 3 is common both in numerator and denominator, so we take 3 common and simplify. After simplification we get dy by dx equals to minus x square plus 2xy plus 2y square upon x square plus 4xy plus y square. Thank you.